Good afternoon, everyone, and welcome to this afternoon's Rothschild lecture, which will be by Professor Peter Bickel, who's standing over at the side there. My name's Patrick Wolf. I'm one of the organizers of the Newton Institute program on theoretical foundations of statistical network analysis. And I just wanted to say a very few words by way of introduction. I came to know Peter through his work on network analysis, in particular, by now a very well-known paper that he published in the Proceedings of the National Academies of Sciences in the USA in 2009, showing how methodologies that come from non-parametric statistics actually have an interesting and, at first glance, rather unusual role to play in the asymptotic statistics of networks. So Peter hails originally from Romania. He has been in the US for a long time, starting with his undergraduate education at Caltech in physics. He went on to receive the PhD from the University of California at Berkeley. His advisor was R.A.Fisher. And the other thing I know about Peter is that he has been married to his lovely wife, Nancy, who is in the back, for more years than I have been alive. So many congratulations to you both. And it's not Peter's first time at the Newton Institute. I think perhaps you were last here for the high-dimensional data analysis program in 2008. Peter has received multiple awards, for example, a Guggenheim, a MacArthur. He's received multiple honorary doctorates. He is a member of the National Academy of Sciences and other such esteemed bodies. And so without further ado, here to talk to you about from small to large data and everything in between, I give you Peter Bickel. Thank you very much.
Thank you, Patrick. I feel I need to correct one thing. Although I started out at Caltech in physics, I ended up getting my bachelor's at UC because I really hated Caltech, so I left after 2 years and finished in 1 year in mathematics. Okay, so I guess I'm supposed to thank not the Rothschild Foundation, but M.M. Rothschild and Sons, I believe, for this lecture, which it's a great pleasure to give it. So this talk is going to be, I didn't really quite know what my audience would be, right? I mean, it's supposed to be a general lecture, but the audience will be mainly, I gather, people from math. In fact, there's very little math in this. There's a couple of formula will appear almost at random. It's mainly my impressions of what has happened to statistics, how statistics has evolved over the years, even from before the time I was born, in fact, and what's happening at present. It's when the subject is to some extent morphing into a major part of this very fashionable word, data science. Okay. So let me start out by small data, where I'll speak, I guess, what I see as the period actually goes way back, to 1945, and then 1945 to 1980. Then I'll talk about big data and data science and some principles leading back to small data and an example. All right, so it's proper, I think, certainly in the UK, to start with a picture of R.A.Fisher, who was, I really view as, despite the fact that I come from Berkeley, as the founder of modern statistics, though of course there was a lot before then. I mean, the method of least squares was invented by Gauss, and Laplace, I think, had absolute deviations even before that. So I'm not going to say too much about Fisher, who, well, a little bit. I'll quote a little bit from him. So first of all, Fisher had a couple of definitions of what statistics was. And this definition, which appears in his famous paper of his in the Proceedings of the Cambridge Philosophical Society is that the object of statistical methods is the reduction of data. A quantity of data which usually by its mere bulk is incapable of entering the mind is to be replaced by relatively few quantities which shall adequately represent the whole, or which, in other words, shall contain as much as possible, ideally, the whole of the relevant information contained in the original data. He was undoubtedly thinking, at least in part, of sufficiency, a principle he introduced, but also of data reduction, which remains with us. In fact, it's been exacerbated. He also elaborated a little bit on, in a somewhat later book. Statistics may be regarded as the study of populations, aggregates, averages, probabilistic models, the study of variation, this is my translation on the right-hand side, testing hypotheses, estimation of features, and the study of methods of reduction, sufficiency of statistics. And I think that is certainly the common theme, at least in my mind. Probabilistic formulation of probabilistic models, and the statistics can't say anything about one object unless that object is very highly dimensional. It can only say things about aggregates. And that, I think, in our times has become just about anything that one can say is only about aggregates. The size of the data that he dealt with was small, or could be reduced to small. So this is famous iris data, which is actually uncharacteristically an exercise in prediction. N is the sample size in standard usage, and P is the number of dimensions, the factors, covariates associated with each object. So there are 50 of those. In Rothamsted, where he did a lot of work on yield of fields, there were typically less than 10 treatments. The yields were in the thousands, but they were quickly reduced to averages and sums of squares. And this is probably essentially unreadable picture, but roughly speaking, just take the curve away to show that in the period that he was working in, which ends about, in Rothamsted, I guess it ends at about 1950, I believe, maybe a bit later, the curve is almost zero. This is some measure of output, size of data, number of experiments, etc. And the questions, as I mentioned before, that he was treating were testing, the null hypothesis, which he emphasized very strongly, one could only contradict, that the treatment does nothing, whatever it is, estimation, things like average yield differences and variations, and classification clustering with the iris data as an example. The methods and models typically were models as simple as possible, and given the types of data sets, they were reasonable approximations usually. Gaussian, when the variables were continuous, the approximations were Gaussian, discrete, Bernoulli, Poisson. More generally, certainly parametric, which is a term he introduced, finite, which can be thought of as finite dimensional manifolds in the space of probability distributions. And I'm listing other concepts that he introduced, p-values, maximum likelihood estimation, and theory. And then this was, of course, augmented and developed in different ways by J.Neyman and Pearson in their work on likelihood ratio tests and confidence regions. Then in the period between 1945 and 1960, you had some new themes entering, decision theory. So based on the J.Neyman-Pearson hypothesis testing and confidence region point of view, Wald developed his broad theory of decision procedures, and then this was developed in both in terms of fixed sample results and asymptotics by Lecombe and certainly Charles Stein and others. Then there was new types of data, which I'm not sure that they were absolutely new, but certainly they were focused on during this period. Sequential analysis, data coming in a series. Wald again played a major role. Jack Kiefer, Hodges and Lehman, Herman Chernoff, and others, and many others. Bayes, of course, has been around for a very long time, since the Reverend Bayes was not quite sure, but it was revived on an axiomatic basis by Jimmy Savage and Bruno De Finetti. And then Herbert Robbins introduced empirical Bayes, which is a conceptually new type of data structure which could be viewable through either frequentist or Bayesian eyes. The classical example was insurance, where you'd be insuring somebody for a year, but you had records of his accidents over a period of years. And so you had an unknown parameter for any given year, but it varied. You could say something about it in terms of its distribution. Then in 1960 to 1980, which is when I actually started getting into the field, theme of robustness arose, which is stability of procedures under deviations from model assumption. And this will come back again. So this was started in a note. Well, again, it was probably much earlier, but it certainly appeared in a note by John Tukey in 1958, developed by Peter Huber and Franz Humpel in the 60s and 80s. And they were, and then more complicated models started to arise from new pursuits, like in survival analysis. Again, I'm citing names, and please, there are a lot of important names which I'm not citing, but I just picked to the extent that I could. So summing up, but with significant exceptions, survey sampling, time series, quality control, the focus of statistics was close analysis of relatively small data sets, and you had plausible probability models and resulting measures of performance in terms of probability of error, mean squared error, and so on. And that was more or less what went on. And then we had the advent of big data, which was in the 1980s. It started, and it's been going on ever since. You had exponential growth in computing power, in sensor types, and in complexity. You had super exponential growth in quantities and types of data. And to show you super exponential, here is a picture from the National Institutes of Health showing on annual scale Moore's law, which in logarithmic scale, Moore's law, which shows the development of the increase in computing power, but here it's actually measured in terms of costs per genome, in costs per producing a genome. And as you can see, that's in some sense the cost which is coming from the computing power, and in fact the cost is dropping even more quickly because of experimental results. And what that translates to is, I think, will be clearer, I think, in this slide. This is an article in PLOS Biology in 2015, which shows you in 4 domains. The one I just want to, I'm interested in are the first and the last, astronomy and genomics. The enormous increase in amounts of data over the years, increases that have happened and that are going to happen. And as you can see, the main thing that I want to stress is the fact that things are measured in zettabytes and petabytes. And a petabyte is equivalent to the material in all US academic research libraries. And an exabyte is 1,000 petabytes, and a zettabyte is 1,000 exabytes. And genomic data is supposed to come in at 1 zeta base per year, and I think it's actually even increasing. And I don't know where the petabases have come, but they're somewhere in this table. And I'm sure, oh, here, I'm sorry, Twitter has 1 to 17 petabases per year. Oh, and the exabase, that's what I was looking for, in storage. That's the largest. Okay, anyway. Now, one of the things that has happened, which is very good, is that in this climate, the focus has been very much on prediction. And it has come really in machine learning, which my colleague Mike Jordan states is statistics, and I agree. It's classification regression used for prediction, but used in ways that certainly statisticians hadn't done before. And the result of prediction and machine learning is, for example, you have movie recommendations for Netflix, ad position for Google, predictions based on past experience. Supervised learning is, in fact, primary. You have a base of covariates, predictors, and outcomes, and then you want to predict what happens in the future if you see the same predictors. What you have, though, what the machinery that's being used is, or being constructed, is a black box, which is produced via algorithms such as random forests, which arose in statistics, or deep neural nets, which has become the great fashion machine learning now, and works as long, and these all work as long as the environment is stable, right? Even prediction isn't perfect. If the population has changed on you, that doesn't help, having learned on a database which is irrelevant. But in any case, the focus is on prediction, not on how things work or why things work, but more on just predicting, which is extremely important. I mean, it's clear that trying to understand why things work and how things work can only follow if you have something which predicts well. Okay, now I gave you an example of the advent. I mean, this one picture of the advent of big data in terms of size. The other aspect of big data is that it's very complex, and it's coming in all sorts of forms. So what this picture shows, I'm not going to dwell long on it, is a project that I was involved in called ENCODE. ENCODE stood for the Encyclopedia of DNA. Its humble goal was to functionally annotate every element of the human genome. It didn't do this, as you might expect, but it did biochemically annotate every element of the human genome, which means you sort of know what it does biochemically, but whether it actually has any function is another matter. And it was an enormous effort and was very useful. And the results, it's continuing, and the results can be found in the Santa Cruz Genome Archive. But as I said, it was extremely complex, right? I mean, so you had 8,000 experiments, 1,700 different assays. And here's a list of the types of assays. The assays, to some extent, all consisted of traces of peaks, but how the experiments were done differed tremendously, and of course, putting them together is another matter. Now, I think it's fair to say certainly Fisher was primarily interested in, and I think it's true it's been sort of the interest of statisticians, in science, in the needs of science. And that means that you want to try to understand causation, you want to understand a small number of predictive factors for specific phenomena, e.g. the genes responsible for a particular phenotypic feature, how these work together, regulation. Ideally, a mechanistic model. I say a mechanistic model. I mean, it's somehow fairly clear, at least to me, that we have these enormous patterns of things which interact with each other. And what we can hope for is little models here and little models here, and then we hope to be able to piece them together. And this is, I guess, the ideal in the end, a hierarchical view of these complex systems. So that's not served by constructing black boxes, initially at least. Here, this, I think I'll skip over this quickly. This is actually taken from a report of the National Research Council in the United States, talking about what data science is. As I said, it's a very fashionable term now. And the main thing about data science is that people are aware now that to get interesting results out of data, it has to be a combination of workers. So the computational aspects are critical, but so are the inferential aspects, so are the, if you want, optimization aspects, the representation, if you want, so all of mathematics is involved. And I feel above all, really, the domain scientists and users of the technology. Because one of the things about big data, as I said, it's so complex, there's so many directions to go in, that without some guidance, you find very little. So I pictured this, I didn't do this for this talk, but another talk, showing statistics in a central role. But really all I want to illustrate is that statistics, I think, at its best, plays the role of a transfer science. That is, you find methods of inference develop in one field, and then if they hold up in that field, they get evaluated, if you want, codified to some extent, analyzed in statistics, and then they transfer to other fields. So that's, and of course it goes back and forth. Okay, so this has resulted in these new emphases for statistics. So a major thing is that computational cost or even feasibility must be considered as much as statistical efficiency. Right? It's no use having the best of all procedures if it takes days to implement, to run. And that's actually been, in some sense, I think, the practical sense of statistics for a long time, that simple procedures are often actually may not be the most efficient, but they're the best, the most stable, and so on. You must work in close collaboration with subject matter experts to determine real questions, weaknesses of data, etc. You have to produce software that is readily available in standard form. And at least from my experience with ENCODE, algorithms and software need to be scalable, because they were not interested in things which couldn't deal with very large bodies of data. I'm saying I'm talking really to the students of the future or even the present. I'm 75 years old, and I have stopped coding quite a while ago. But I can at least appreciate what the problems are and what the issues are. And since I realize that this is largely a mathematical audience, I have to say something about math. So you do face new theoretical challenges from asymptotic exploration of high-dimensional space. That's the thing that I'm most familiar with. There are concentration phenomena, random matrix theory is become highly relevant, and mathematics, such as the one we've been discussing here, relevant to complex, new, or newly abundant types of data, such as networks. And I just wanted to illustrate, so this is the only bit of notation in the talk. Well, there may be one tiny one after this. And it's just to show that mathematics does play a role. So this is one of the most standard statistical models, which is that you have observations which are vectors, xi, which consist of a set of covariates or predictors, zi, a vector, and yi, which is an outcome which can be real or categorical. In this case, it's assumed real, and if you have one observation, this is I should really see how this thing points. Yeah, this is the model that you tell yourself. Y is a linear combination of the z's plus error, and actually this assumes that the error is independent of z. That's actually not necessarily true, but at the very least, to make any sense of this, you want the conditional expectation of the error given the covariates is 0. And then you're making the further assumption that the conditional expectation of y given z is linear in the covariates. And these are both large assumptions. But anyway, they're very standard, as you know, in statistics, or many of you know. Now, usually the way that this problem, the problem of getting at the betas, I'm sorry, maybe I didn't mention, but of course you have n independent copies of these things. Of solving this is that you do least squares, right? You minimize the difference between the observed yi's and the x transpose or z transpose betas using Euclidean distance. This is fine, gives you a nice explicit solution. But unfortunately, it is not resistant to gross errors. So if somebody makes a mistake, a serious mistake in your data, right, not in the z's but in the y's, the whole thing can be thrown off entirely. And so as a solution to at least part of this phenomenon, Peter Huber proposed in the 60s that one should look at minimizing other measures of distance. And the actually, interestingly enough, I think as I mentioned earlier, there is one of these measures of distance, which is the absolute value, was in fact considered before least squares by Laplace, who concluded that computation was a problem. And so Gauss said, well, use least squares and then you get an explicit solution, but actually the absolute value thing is indeed much less sensitive to gross errors, to perturbations. And then you get, if this is strictly convex at least, it's not, for absolute value you get a convex set of solutions, but let's say this is strictly convex, then you get beta hat as a solution. It's not explicit, but there's many, many ways of obtaining it. I mean, since you're minimizing a convex function. And then there's a result under mild conditions, which says that this estimate is equal to what you want to estimate plus something linear plus smaller order terms, which the conclusion being that this thing is asymptotically Gaussian, with a variance which is very nice because it breaks up into something which depends only on the design, the variance-covariance matrix of the design, and the psi function is the derivative of rho. This is the feature of the loss function. So for example, if you use L1 distance, psi of t is signum t. Whereas if you use least squares, it's t itself. Okay. So that's not surprising. That's all well known. But the surprising thing that I encountered recently, and that did indeed require a lot of modern theory, if you want, concentration theory, all done by Nuruddin El-Karoui, but also later by Donahoe and Montanari. You ask what happens if, in fact, as is not so uncommon nowadays, the number of parameters is comparable to the number of observations, right? All the examples, all the results that I've given were for p fixed or p over n tending to 0, it is sufficiently fast. And if you assume sparsity, which I'll talk about later, then things are okay. Without sparsity, prediction of beta becomes lousy. It's of order 1. But you can actually still talk about estimating individual coordinates, any number of individual coordinates, which is of interest. However, things go badly wrong in the variance. The variance now starts to involve the errors, the loss function, the distribution, the distribution of the errors, the loss function, and the design in a quite complicated way. And actually, of course, it turns out that when you start to simulate for p comparable to n, this is a much better approximation than the one that you get from just assuming Gaussianity with the variance that you normally get. This is a very strange phenomenon. It's only true for certain class of designs, but it's certainly a feature of high dimension. Very much so. This is all true as p and n both go to infinity. Okay, so that's the end of the math. Now, what I actually view as the big challenge that we're facing is that since the data from the beginning lives in a very high dimensional space, right? It's not that you have a lot of observations. I mean, once I remember when I was young that I was talking to some physicists and they said, well, you know, if you have a lot of observations, there's no problem. You know, you don't need any statistics. You just compute and that's it. Well, the trouble is that when you have a lot of observations, you also have very complex structures. And you're only interested in parts of the structures. And the parts of the data which bear on the structures may actually not be so large. But So we want to say specific things with some level of confidence about low-dimensional objects, which corresponds to small data sets, right? But now we have a difficulty that Fisher didn't have. We need to find them. You have the needle in the haystack problem, right? You have a lot of stuff which is uninformative surrounding the structures that you care about. Okay, I'll give you some examples in a second, but let me proceed with some basic principles or beliefs, because if those principles are not right, we probably are sunk. But to get successful inference from big data, it would appear, and in a way the result that I cited before tells you that, it will appear that you need sparsity, which I will be a bit more explicit about, but for the question we're asking, there's a low-dimensional approximate representation of our data, which is interpretable. You also really need stability. To have confidence in your conclusions, algorithms, models, and procedures, they need to be stable under plausible perturbations, right? One of the perturbations is, one of the perturbations, as I said, gross errors, but there are many others, right? So if you think that there's some things that can happen which might have the noise or the structure be a little bit different from what you think it is, it had better be that your algorithm doesn't move too much in its conclusions when you do that. And finally, this is, I actually think, at least from my experience with working in genomics, that at least I should say really in the big data sets that I've been working in, the noise levels are such that the conclusions are credible only if you have really high signal-to-noise ratio. Okay, so this is the other little bit of math, just to make these definitions be a bit more formal. You have a random object, vector, matrix, etc., distributed according to P, a probability on omega, some sample space. You have our model, that's a set of P's that we hypothesize. And then we have the parameter, an aspect function of P we're interested in, which is itself a vector, matrix, etc. And again, I'm giving you the same example just for convenience, and also because I can then talk easily about these concepts in that. Now, what do we mean by sparsity? Oh, sorry, I think I may have, oops. Sorry. Okay. So a sparse model is one describable in terms of sparse parameters. So for example, if n and p are large, p being, remember, the number of parameters, p much larger than n in genomics, we hope that beta is sparse. What does that mean? That means that the number of factors which bear on what you're interested in is small. Most of the betas that appear in that expression in Z transpose beta, most of the coordinates are 0. And notice that the regression model in this case is itself only an approximation to the actual data producing mechanism. It's typically not linear, but beta still can be interpreted as measuring relation of y to z. And what I'm saying is that having sparsity for this particular parameter, beta, this is really consistent with Fisher's original description. You want to end up from this huge body of data to have a small set of numbers that you can wrap your head around. Further examples of sparse parameters, it's not limited to things which have a lot of zeros, obviously. It's, of course, can be a function approximable by a small number of basis elements. It can be a big matrix approximable by one of the same size but lower rank. It can be a big matrix approximable by one with few non-zero elements. And of course, and this I'm speaking not from knowledge, but from hearsay, but it's hearsay that I believe. Sparsity is critical in computing from the point of view of storage. I can even imagine why that is. And optimization, convergence as well. Okay, so as I said, the big problem of big data is we don't know where the zeros are. And finding them involves minimizing a penalty. Now, an objective function plus a penalty. Now, the natural penalty, sorry, I didn't mean to do that. Yes, is the number of non-zero elements. However, what that means is that you have to do a combinatorial search, right? Since you don't know what the positions are, you have to search over all possible subsets of positions, and that's usually impossible. And there is, fortunately, in many cases, a solution if there is sparsity present, which was pioneered by Dave Donahoe first, and then Immanuel Candes and others. It started in the 1990s with Dave and is going on for the present. That is, you replace the norm 0, that is the number of elements, by norm 1, or the nuclear norm, the Schotten 1 norm. All of these can be viewed as convex approximations to norm 0. For a survey, which I think people will enjoy, there's a paper of Immanuel Candes in the International Congress of Mathematicians in 2014 called The Mathematics of Sparsity. Now, stability. Well, I would like to quote a colleague of mine, Bin Yu. Statistical stability holds if statistical conclusions are robust or stable with respect to particular perturbations of the data. That is, statistical stability is defined relative to a particular aim and a particular perturbation. That is, you cannot find something that is stable against all perturbations. You have to make up your mind what you want to have the thing stable with respect to. So some examples. In the standard method of estimating beta, for sparsity, you add the L1 norm, as I think I indicated earlier. For stability against gross errors, you don't put the L1 norm as a penalty, but you replace L2 by L1 in the objective function. So it's not as a penalty. For stability in choosing this tuning parameter lambda, you often sample split. You fit on one half and you choose lambda on the other. And then there's also actually stability for both Bayesians and frequentists. I didn't mention much about Bayesians, and I'm not sure that I will. By now, I think the distinction is almost non-existent, though I'm sure there are people who in this audience who might disagree with me. But of course, the issues come there too. For example, is the posterior stable? That was already considered by George Box in 1980. So a prior which gives you an unstable posterior, for example, a posterior which is quite inconsistent with the data, or puts the mean, let's say, at a position quite inconsistent with the data, is somehow disturbing. Here I'll give you a simple personal example, a very short one. It's really stability in the large, but I'm giving it to you because it was one of the first problem that I dealt with in the ENCODE project, and which actually has a fair amount of mathematics in it, but you can't tell from this. So the problem was you were given two biological replicates. As I said, there are these traces with peaks, or things which look like peaks, but determining a peak is not such a simple thing. So there were, at least at that time when we were working, 10 algorithms for determining peaks, and they all came, they all had different tuning values, they all came with somewhat different answers, right? And so the question was, how could you choose, since this was a large operation, you wanted to choose a method which was stable so that, different labs didn't come up with completely different answers. And that was essentially what we did. We determined a method which actually told you how far down the peak list you should go. And then the further down the peak list you can go, in some sense, the better the algorithm. Finally, let me close. I see I'm finishing this in lots of time. I'm early, yes. I'm going to continue to be early. I want to tell you about a successful application of these three principles of stability and sparsity and strength of signal. It's actually, I'm saying it's successful. It's in progress. But up to this point, it's, at least I enjoyed it. So the problem is the following. You have data on 426 subjects who have different cholesterol levels, which have been measured. And for each of these subjects, you have expression for each of 8,000 genes. That's under the same conditions. And now what you want to do is you want to identify genes playing a role in cholesterol metabolism. So one way to do it is to look at pairs of genes and get a measure of co-expression. To what extent do they go together, in some sense together with the variation in the cholesterol. And so what you do is for each of these patients, I think that's on the next slide. Oh, well, here's the data. One has to always give a thing like that. Normalized RNA sequence data from a study, and these are from a mixed Caucasian African-American group of people, and it's a particular cell line. So having noted that, we can go on to the next. Oh, I should have stayed where I was. Okay. So I have to give you a measure of the co-expression of these two genes. And so the measure of co-expression is the Spearman rank correlation. So how is that done? One of the problems is that the actual values of expression for genes are not, it's across individuals, for example, are hard to compare. So the first thing that was done was that each expression of a gene in an individual was replaced by its rank in expression among all genes, right? So you look at gene 1, and then you look at the 8,000 genes. They all have expressions. Where is gene 1 in that series of expressions? And you assign its rank to it. What that does is it makes you invariant to monotone transformations, which you don't know. And then you have these pairs of ranks now, one for each of a pair of genes. And now you form a standard correlation, for those of you who know that, which I presume is most of you. It's a measure of the relation of these two things. Okay, so what do we do? So now we have these 8,000 guys. So one thing, or 8,000 choose 2 guys rather. What you do, or what we did anyway, was to use a method called spectral clustering, which is described in Ng, Jordan, and Weiss. So it actually can be based on a generative model. It's spectral clustering of a version of the Laplacian, the so-called normalized Laplacian. So D is the diagonal matrix of no degrees, and the Laplacian is, those should be minus a halves, not a halves. There. And then you do an eigenanalysis of these things, again, for those of you who are not from math departments. Basically, what you're doing is you're taking this matrix and you are replacing it by a much lower dimensional matrix, namely that corresponding to its first k eigenvectors. So the k eigenvectors form an n by k matrix, right? And now what you do is you change positions, and now you look at these as kn vectors. Sorry, no, not kn vectors, nk vectors. And now you cluster these. And the idea is that these k vectors, rows or columns, I guess they have to be columns. No, rows. These guys can be sort of viewed as low-dimensional representations of the full n vector. And then you cluster them by k-means, or other ways, but the standard way is by k-means. And we did it, and this is what we got. Well, you say, well, there is something here, right? I mean, but there's much too much of it, whatever it is. And we didn't dare take those genes in the handle and present them to the biologists we were working for. Or maybe we did, I can't remember anymore, but in any case, it was no use. So what did we do? Oh, I think this is jumping. Oh, dear me. Spectral clustering. Oh, gosh, I think one of the slides may have gotten lost. Let me just keep on going and see if I can find it. Yes. Oh, no, I'm sorry. I apologize. I was the right place. I actually, this was the first step. Okay, so what did we do? So what we did is we said, well, obviously we've got trouble because this thing is so big. We went to the biologists and said, can you present us with a small list of things that you think are associated with cholesterol? And there's something some of you who are in biology may know called the Go terms. And the Go terms tell you, you know, somewhere, somehow this thing has been associated with some feature, and in particular cholesterol. But usually most of these things are not worth very much. So, but they came up with 80 genes or so. And then we did the same spectral clustering on the 80 genes. And lo and behold, you get something. You got a very clear cluster of genes which they immediately recognize as being a pathway. So the pathway for cholesterol production. And the others, you know, may be relevant to other features, or they may be relevant to nothing. All right. So that was already somewhat comforting, that there is some signal there, if you just look at it right. But the trouble is, of course, they knew these already, right? I mean, it's nothing terribly novel to them. So we decided to go fishing. And so how do we go fishing? We randomly, repeatedly selected blocks of 920 genes out of these 8,000, and each time added the 80 cholesterol genes. So instead of 8,000, we have 1,000. That turned out to be enough. How 1,000 was chosen, I can't tell you. And in fact, it should have been optimized, but it wasn't. And we clustered each of these many randomly repeated blocks of 1,000. And in all of the sets, though I'm not actually quite sure of that, but that was what the student reported, the 80s form a cluster. But in 13 of the sets, you found a new gene, another gene, clearly in the middle of that cluster of 20. And actually, these were all confirmed. All right, so many of the 13 were identified as being in the lipid pathway, above the cholesterol pathway. And actually, we just confirmed all of them with a different data set. And some of these are still not known. So here's the gene fishing result. And that's it. No, wait. No. Closing remarks. Okay. This is really sort of my summing up of the passage of time, if you want. So I think statistics and machine learning are becoming the same field, with machine learning focusing primarily on prediction and computational issues, statistics primarily on inference and asymptotics. But together, they function as a transfer science within data science in all aspects of human inquiry. And both actually, in fact, somebody to be a co-statistician and machine learner need all the skills in the first two bullets and close ties to applications. I think both need sparsity and stability. Prediction works even if the effects are due to many weak sources, but it helps if there are relatively few strong sources. And mathematically, there are new problems and surprising phenomena that appear. And, well, 10 minutes early.
Thank you. We've got plenty of time for questions and plenty of audience members, so just so the microphone picks you up, I'd say please speak your question relatively loudly, but we're now open for questions from the audience. So who'd like to ask the first question of Peter?
May I just add, just to make it easier, that I would be very glad to have issues added or important points added to this list that I put down earlier. Or things that I missed.
So I'll ask the first question, and it relates to your list. We all know as we teach undergraduates and postgraduate students that it's hard to cram more and more material into the same amount of time. If we can't ask our students to absorb all of statistics, all of machine learning, and all of working with application domain experts, what do you think the statistician of the future should look like?
Well, as usual, I think things will depend upon which university the statistician goes to, as far as which aspects are emphasized, which people in which applications people work with primarily, or whether people do more pure mathematics. Yeah, of course, you can't do it all, but in some sense, if you're going to do applied statistics, at least, or machine learning for that matter, you should at least have some pieces of that. Yeah. And, students do choose, so.
Thank you. Questions? Yeah.
Some people that I know say that machine learning is just a word which is the same as statistics but used by computer scientists. When you're using it, it appears differently. So what's your definition of machine learning, and how does it differ?
Oh, the difference, as far as I can see, is that it came from a different group of people. It came from people who for example, were largely computer scientists and were very familiar with computational issues, which most statisticians weren't. It also came from what was I going to say? Applied mathematicians, physicists who were working with algorithms in applied mathematics, which had nothing to do with statistics. And so some of the algorithms that evolved, although they were, of course, in the end, if you want, classification or regression, in fact were different. I mean, there were things that would not have come up naturally out of the statistics community. And so I make the distinction in that sense, that the emphases were different. And I don't really care very much whether things are called statistics or something else. What's important is what people actually do.
The support vector or whatever is another discrimination method.
What?
Support vector, what are they called?
Support vector
machine, so the word machine. So it's just a discrimination method. So it comes from someone else, but for me it's the same. Same
Yeah, but what about neural nets? Is that something that you think would have easily come up out of statistics?
No, neural networks is a somewhat different story.
Yeah. Or boosting, for that matter. There's things done which seem totally illegitimate from a statistical point of view.
Yes.
But they work. And then you can analyze and see why they work.
Peter?
Yeah.
So you're arguing that you need sparsity
Yes.
in order for this to work. So you impose sparsity in an algorithm. How do you decide, how do you know whether or not what you find when you've imposed sparsity and obtained results, seemingly important results, but imposing sparsity in your algorithm doesn't make sparsity the case in the data?
No.
So that seems to be one of the main problems here. I mean, you find something under the assumption of sparsity, and the ability to tell whether that's an artifact or not is a sticky wicket.
That's right, and it's always been a sticky wicket. And you just try to, you try to do sample splitting and things like that to get by it. I mean, in the end, at least the thing that would make me happy is you found the right variables, right? Or you with the lasso, for example, which we know is bias, right? So you find the right set of variables, or a set of variables which contains the right set of variables. It's not too big. And then you proceed to act as if these were the only variables you needed to consider. And in fact, if you're right, with probability tending to 1, inference is legitimate.
Right, if you're right.
If you're right. Well, but that's true of anything. Right? I mean,
Right. And in this case, so in some situations, however, simpler cases,
yes.
mathematics has been developed to help you determine that without doing, data splitting, without having to do computation. And do you see any reason to hope that there's going to be a mathematical attack on this problem in the sparsity case?
Well, yes. I mean, if you look at Candace's work, I mean, there's a great deal of mathematics in that. But I think, as usual, in the passage from but this is now my own philosophy, as most of this has been, in the passage from mathematics or statistics even to applications, you can never be sure. Right? I mean, the conclusions are always dependent on some hypotheses, right? And in fact, I think the real strength that one gathers is from other data, right? Not necessarily the same type. Other things that bear on the same conclusions. So I guess I always view, sure, all sorts of mathematical approximations are fine. And you make them, and you produce conclusions based on them, but I always take them with a grain of salt. Yes?
Earlier in the talk, you mentioned random forests.
Yes.
And I think that was the only time you mentioned the word random.
Oh, no. Not explicitly. I mentioned sample splitting, which is, of course, random. Yes.
Would you like to say anything further about the importance of randomness in modern methods?
Yeah, I mean, there's a lot that I don't know, and know only by reputation. But the bootstrap, which is Monte Carlo in the service of inference, is sort of a general tool. Whenever you have something which is too complicated to compute, you Monte Carlo it, and that's true, I think, not only in statistics. I mean, after all, Monte Carlo was originally invented, I believe, for problems having to do with the hydrogen bomb, and the algorithms which have actually made Bayesian inference, for example, possible, Markov chain Monte Carlo, came from a paper in the early 1950s by a group of physicists which included Edward Teller, I believe, and Metropolis and others. It's very important, and I know that it's also, probabilistic models, I think, are but again, I'm talking about repute rather than anything else, are playing a role in a lot of mathematics, right? Not just mathematics relevant to statistics. And so, on the one hand, they're important applications. On the other hand, they're important in theory. And maybe it's just telling us that we better start thinking about the world in the way that I guess the physicists were forced to by quantum theory.
It's just coming up on 5 o'clock, so I'd suggest maybe one last formal question, but then, of course, Peter is in the building, and so we're welcome to carry on discussions informally. But one last question for Peter from anyone on the floor.
I was interested in the cholesterol model. If you hadn't been able to get that input already on the selection of the group, would you have made any progress?
We might have tried we might have tried other
So is
things.
that going to be a common situation, you think, with big data, that you need that?
No, not well. It's hard to tell. I mean, there are also huge machine learning engines which have been built, Bayesian engines, which screen and claim all sorts of things. And in some cases, I'm sure that they pick up some correct things, and maybe those can be a starter if you want. But they also pick up a lot of wrong things. So yeah. I mean, if you want, we still have an issue now. Okay, so we found these guys. We want to continue fishing. So we want to construct some sort of algorithm, which at least I do, pushes out.
Well, it's just interesting to me that you have the mathematical framework, but then you have to something that's come from outside mathematics. Is actually fluid to hanging that together.
Yes.
Okay, well, please join me in thanking Peter again.